Assalamualaikum warahmatullahi wabarakatuh and very good day. Welcome back to Mechanism Design. So this will be a video on the topic of cam and follower design. Alrighty, let me share my screen. So let's start from the beginning, especially for those who did not come or attend the first time when we started on this topic. Which is a very cool topic. So cam is also known in Malay as sesondol, or I guess sesondol, and I guess using cams is much better. Cams and followers, because it needs to go hand in hand. So for those who have not seen a cam yet, so this is a cam. These are some examples of cams and how they work. So the one that is rotating is called the cam, whereas the one that is moving linearly is called the follower. There are many types of followers, and they are usually always in contact as the cam turns. On the left here, you can see how this cam can also be the motion of the cam and its follower can also be replicated or be replaced by a slider crank. So slider crank is the basic linkage mechanism, and you always want to try to solve the problem using slider crank first, because it is of the linkage type, and linkage type is I guess the cheapest solution, the most expensive solution in mechanism, whereas the cam and followers will be the most expensive one. So if you talk about cost of designing and things like that. All right, so one of the main thing when we talk about cams is that we need to know the displacement diagrams. So we have to create, or we have to understand a displacement diagram, because this is the shape that will be followed by the follower. So this thing is being open and expanded in a flat manner. So instead of it being a circular in shape, so this one is expanded, and we plot it in terms of the degrees or the angles of rotation in the x direction, whereas y is the displacement or the delta y measured from the center of the rotation of the cam. So the basic shape of the cam is based on a circle, but if it is complete circle or a perfect circle, it's not a cam. It must be a non-circular shape. Okay? A cam is a non-circular shape, but it needs to have a base circle inside of it. So all this displacement is with respect to or based on a certain base circle radius. Okay, So even if you plot this one, start from 0 in terms of y, so that 0 is from the surface or from the perimeter of a circle. All right, so there are many faces in the displacement diagram. As we go from the left to right, so when you go uphill, this face is called the rise face or rise motion. And then when it is flat like this, from left to right, so this is a plateau, meaning it is maintaining at that position, current position. And then when the curve goes downhill, so it is fall, it's called fall motion, falling motion. Then we have this plateau again, and then fall motion. So the type of motion are numerous. There are numerous types of motions available. Some will look something like S here, but there are specific names for this kind of motions that we will talk about in a bit. So these are some of the places where we can see the use of cams and followers. Notably, they are mainly used in engines, a lot of engines and machines like that. So in order to control the valve opening and closing, so we can control it by using cams. So this, as you can expect, is no easy task because you need to know the timing of this. So it's used for timing. It's used for timing. Needs to be related to the motion of the crankshaft in the engine. So that is connected by this belting system, timing belt. Then these are other types of cams. You can have plate cams, drum cams, and linear cams. So you can imagine how they are utilized. And some cams are being used in something simple, such as clamps. Okay, you can have a cam in clamps or in something for locking mechanism, locking devices. So usually it is between something that rotates and another rotating. Then but the more common one will be something that rotates, and the other one, the follower, will be in the linear motion, same as this one. All right. Other interesting facts, we can have cams that are inline, okay, where the motion of the follower will be, we can relate to fall onto the center of the rotation of the cam. But we can also have offset situation where this line of action for the linear motion will not pass through the center of rotation, such as this. And if you can see here, in terms of shape of the follower, we have knife edge, flat face, this is roller, and this is something like spherical. Okay. All right. So usually the situation will be involving the description of the cam, such as this one on the top left. So it'll tell you how the cam behaves, and so there'll be 1, 2, 3, and or more. So it will tell you how it will behave for one circle, one revolution, one rotation. So in this case, will rise outward, meaning this is outward from based on the base circle that you decide or you choose, and that rise will be 1 inch, and it'll tell you the time taken, and you can correlate this to how many degrees of rotation of the cam. Then dwell, it tells you the next behavior will be a dwell, so meaning it maintains 1 inch from the base circle, okay, 1 inch radius from the base circle, delta radius, and this takes 0.2 seconds, and then it will fall. So meaning this thing will fall back down to the base circle. So meaning it will fall this much, 1 inch, and that interval will take 0.5 seconds. Okay, after you have understood this motion, you have to create your displacement diagram. So displacement diagram, after you have done that, then only you can create your profile, cam profile. Yep, that's the kind of things that you are expected to do. So some of the things that you have to calculate will be the angular rotation, angular velocity, omega of the cam. Then you have to get some conversion between time, because usually that behavior or motion is described in terms of times, and you know that the total time that will describe the full 360 degrees rotation, and then you have to find what or each of the time interval in terms of angle of rotation, how many degrees it takes instead of just about the time. Then and then there'll be this kind of things, actual manner of to achieve the displacement. Okay, so yeah. So motion schemes, there are many, and this one will be the first one. It's called constant velocity straight line. So meaning this one will be in the displacement diagram. Okay, you'll see this shape in the displacement diagram, and the follower, whatever that shape of the follower, will just go up this shape that is drawn here. This is for the rise, and this one will for the fall, rise and fall. Okay, and this will be the equations describing this line, and this is for displacement. So I'll talk about this thing, and always there'll be two sets of this equation. One is if you are using time, and then two if you want to use in terms of angles. So this is the less time or less theta for this interval, and this is the first point for the in terms of time, and also in terms of angle for this interval. Okay, same over here, and you have h naught will be the radius of the base circle. So this one will be here if you are not taking 0 as the starting line. So that will be for the motion, for the displacement on top. Second row will be for the velocity, and the last row will be for the acceleration. So constant velocity meaning when you look into the velocity, the diagram will be flat, flat, and it's constant velocity. And the value for the acceleration will be 0 over this flat region. Okay, I believe in the class we look into this problem. If I can stop that for a second and go with this part, put over there, and then this part here. So constant velocity, I guess. Here we in this template, there are a couple of things that we can change, such as dt time. You can change it to 7 because if you take 3 seconds plus 1.5 will be 4.5, and then add another 2 seconds, 4.5 becomes 6.5, and then plus this 0.5 will be 7 seconds. So dt will be 7 seconds, and that relates to here omega will be 2 pi divided by the time, 2 pi divided by the time, so it'll be in radian per second. And then you can relate that to this theta, time to theta. So because in the original question gives you like this is 3 seconds, so 3 seconds will correspond to how many degrees? So you have to see that. So I guess if for that delta is 51.42 degrees per second, so meaning if you take 3 seconds, so that will correspond to 154.3, 154.3. And at the boundary between two motion, like between rise and dwell, so you have to have double, because at time 3 seconds, there is a part that follows the previous or the first motion, and then at that same time it follows the next motion. Okay, so at time 3 seconds you have to and make sure the value there will be the same in most cases. That value must be the same. Okay, must be the same. I mean this one. So this one is dr. And here we also have set what is the base circle radius. So I just put one inch. So everything will be based on that 1 inch. Okay. So in this case, the center of rotation will be here, and you can imagine the circle over here. And so we just have to put in that equation right into that. All right. So if you have other types of motion, so you have to follow that their respective shapes and the corresponding equation. So some motion will be more complex than others. Okay, but I guess it's a good if you can try to use the template and try to do it. Okay. So if you have problems and don't understand how to use it, let me know. And the next one is this how to draw it. So like I mentioned in the class, a lot of this topic can be found on also not just in mechanism book, but also in drawing books, because in the past designers will have to draw this thing. So that's why they are prevalently usually also found in technical drawing or engineering drawing books. So in this case, if you know, the cam will rotate in a clockwise manner like this. Omega cam will be like that. But when you draw it, you have to draw or construct this thing in the opposite way. Okay, so that's I guess you can think about it why we do such a thing. Okay, so if you know the omega of the cam is clockwise, so you construct this thing in the counterclockwise manner. Okay, is you got to go opposite. Okay, because as if this thing will follow this shape, such as this one. So you can create a few points here. So this one creates points every 30 degrees of rotation. So 30 degrees will be here. So as you see, this one will be delta R at 30 degrees. Okay, so you have to go back to to your displacement diagram, get your delta R at 30 degrees and draw the point over there. So this one at 30 degrees, get that point, 90 degrees, 120, and so on and so forth. All right, so this is a situation where it is inline. So you can try to so do this maybe in the class next time I'll show you. So here the most important thing is for you to know the cam angle. It needs to be from 0 to 360, and then the delta R. So preferably this delta R will also include from the center of the rotation, not just the delta from the from the base circle. So this is another situation where the follower is a roller type. So roller type, you have to take into consideration the radius of the roller. So the center of the roller radius, roller will be the trace point. So that will be just another offset from the real cam profile. Okay, and then we have the offset situation. So offset situation will be like this. So you have to draw some angles, and that angle will be this offset, and that one will be at 0 degrees, and then 30 degrees will be like that. So you can try to follow this method or SOP in order to construct a offset cam. Okay, so the next one will be cylindrical cams. So this is also interesting. So this one is like the cylinder is uh, taken apart and flatten out, and it'll show this shape. So it will still go. You need to consider from 0 to 360 degrees. Okay, other rigid body mechanism that will be of interest will be like ratchet and pawl. You can see in a lot of machines, such as in tools, power tools, in hand tools, in something like this. Maybe if you have, if you are into rock climbing or something like that, maybe you'll see this kind of things being used for supporting body load and also for supporting other kind of loads. And then you have this intermittent motion mechanisms such as the Geneva cams, indexing mechanism, and barrel cams. So these are also very common in a lot of machineries. Okay, so this is how they work. And in this case, they are 1 degree of freedom system. Okay, this is how Geneva cam is can be designed or analyzed. And we can also have walkers such as Theo Jensen and Klein, and a lot of other can find out about them. And they are complicated and can be used for building some interesting machines. The walkers. So we also have like Strandbeest, Trotbot, Strider, Klein. And that's about it, people. That's about it. Maybe inshallah I'll see you in the class and we can talk about all this work again. And yes, try to do the homework. That will also include a question on cam design, and try to construct the displacement diagram as well as the cam profile. You guys have a great one. Assalamualaikum. Bye-bye.